Thank you all for joining our monthly seminar series, Asia US, for the Association of Computational Mechanics. So today we have two great speakers from Asia, Wentao Yan, and from the US, Steve WaiChing. So we started with Wentao Yan. So Wentao Yan is an associate professor at NUS, Department of Mechanical Engineering, and he was previously a postdoctoral fellow at Northwestern University in the US, and he received his PhD and bachelor at Tsinghua University in Beijing. Wentao, the floor is yours. Thank you.
Okay, thanks. Thanks for the invitation. So today I'll mainly talk about our work on modeling of additive manufacturing, from like physics-based to AI-driven modeling. Today I'll mainly talk about this most popular additive manufacturing technique called pod bed fusion. So the basic idea is very simple. Just apply one powder layer, and then second step is just to selectively melt the powder. So actually, it's a 3D accumulation of 2D cross sections. That's a basic concept, right? It's very straightforward, and the advantages are also very well known. We can fabricate very complex structures. There are a lot of freedoms to control microstructures and the mechanical properties. Then, in industry, there are a lot of advantages. Say, for turbo blades, we can control it to be columnar grains or even single crystals. And for material science, it opens new way to design and synthesize new compositions. For example, we can combine any unique powder combination, then we can get the chemical composition we want. And we can even control the chemical composition at different locations so that we can make sure in each location, the chemical composition, the microstructure, and the mechanical property are the optimal. Um, but the problem for additive manufacturing is one, there are a lot of defects, and we do not really have clear understanding into the mechanisms. Second is the quality inconsistency, because current additive manufacturing is still open loop control. The in-situ monitoring and closed loop control are still in a very early stage. And thirdly is in real industry applications, people rely on very heavy trial and error experiments to get the optimal manufacturing parameters. For example, so this is uh, the foldable cell phones. The hinge is 3D printed, and this company work with the 3D printing company. They develop this. They spend 18 months to find the optimal manufacturing parameters. So why they are so slow? Because they rely on trial and error experiments. So our research objective is we want to use computational modeling to understand the physics mechanism. That's first. Second is we want to provide guidance to the selection and optimization of manufacturing parameters. And in the long term, we want to synergize the hardware and software together for closed loop control. But today I will mainly focus on the first part. So the overall modeling workflow is like this. When we have fabrication parameters, we simulate the manufacturing process like powder spreading, powder melting. Um, then we can get almost everything, every parameter or every variables in this process. Then we implement into the microstructure evolution models using, say, cellular, automaton, and phase field models. We can get the complete information about structure. And then we can use crystal plasticity model for metals to predict the mechanical properties, including strength, fatigue. Uh, but we will mainly focus on thermal stress and residual stress because this is the problem that is most difficult in industry. Then we can evaluate the mechanical property from the manufacturing parameter through this simulation workflow. For this melting process is very complex. The key physics include one is the Higgs model. For laser, we usually use ray tracing model. And for electron beam, it's a penetration. So it's different physics. Secondly, is alloy evaporation. It will induce mass loss, energy loss, and recoil pressure. But more complex is the temperature and composition will determine the local alloy evaporation rate. And also in the process, we cannot avoid multi-material. Say, for example, liquid gas reactions, in-situ alloying, which is liquid reactions, and also some composites. So this involves chemical reactions, mass transport, and also all the properties like melting temperature, thermoconductivity, specific heat are all dependent on local chemical compositions. And also people at external fields like magnetic fields and ultrasound. Uh, Lastly, it also involves very complex multiphase flow, uh, like powder droplet gas vapor interactions. So I'll go through this very quickly. So for the heat source model, we track the multiple reflections of the laser within the material surface. And for each reflection, we calculate uh, the local energy absorption. This is some verification case. And for electron beam, we simulate the collisions between free electrons and atoms. And this is like 10 million free electrons impinging into the materials, uh, have collisions with atoms, and these are trajectories, uh, absorbed energy, and energy loss due to backscattering. And then we can get the Higgs model from the fundamental quantum physics with no assumption. Then we implement this model into metal scale, which is in powder scale. So we first reconstruct the free surfaces, and then we divided this uh, laser or electron beams into a lot of rays, and then based on the local incidence angle, every location the incidence angle will be different, and the energy absorptivity will be different. Then we'll apply the absorbed energy along the penetration depths for electron beam, and also or for laser we consider the energy absorptivity on the surface. And also apply the recoil pressure, which is dependent on the local temperature and local chemical compositions. And for our model, the mesh size is about 5 micrometer, and the time step size, now we make it 50 nanosecond, which is sufficient for the best experimental validation for now. So there's some verification case, the melting of spherical pod particle. And also for Gaussian distribution, this is a energy distribution in the cross section, and you can see the temperature can be even higher than the boiling temperature, so there will be very strong evaporation. The recoil pressure will dig a hole here. Um, so for the alloy evaporation, we develop our own model from the fundamental thermodynamics. For example, the Maxwell distribution equation for molecules and Boltzmann equation for molecule collisions. Uh, the major motivation for us to develop this model is because we realized the previous very classical model developed by Annie Smith in 1970 is oversimplified. They do not consider the influence of chemical compositions, and we consider the influence of chemical compositions. More specifically, we consider different chemical elements will have different evaporation rates under the same condition, temperature and ambient pressure. And this is the experimental validation against the in-situ X-ray imaging by Argonne National Lab. And you can see this is the keyhole from the first initiation to steady state. It takes 70 microseconds. For our simulation, it takes 75 microseconds, so it's very close. But if we use any smooth model, it cannot even reach this state after 100 microseconds. So basically, our model is incorporate more physics, have wider applications to different chemical combinations. And with this, we can further simulate how this uh, strong evaporation, this keyhole dynamics will influence the defects generation. So this is also by Argonne National Lab. So you can see here, this is the observation of the keyhole dynamics. Um, this collab and then generate a pore here. This is our simulation, and we reproduce every stage during this process, the protrusion process, then the newborn keyhole, and then the keyhole collab generate a bubble, and this bubble will be trapped by the solidification front, which is liquid-solid interface, and then become a pore in the final part. And we review the underlying mechanisms from this recoil pressure, which is the driving force. And from the energy point of view, is because of the fluctuation of energy absorptivity. And we can also predict the pore size under different manufacturing parameters. Um, and to show that our model really consider the different evaporation rates of different chemical elements. So this is one case. Uh, this is one high entropy alloy, and we initially assume the chemical combinations in the base plate and in the powder are consistent, are uniform, and we use different manufacturing parameters to do the melting. And you can see because of the strong evaporation, uh, the concentration become lower, and different locations have different reduction because different locations will have different temperature at the bottom. The temperature is the highest, so the evaporation rates are the highest. So the loss rate is the highest. And due to the very quick solidification, there is no time for the bottom region to mix with others. So the bottom remains the lowest in the chemical combinations, and different manufacturing parameter will give us different results. And this is the experimental validation. You can see originally it's 34%, and then with different manufacturing parameters, it can reduce to 33, even 31, um, so which is significant reduction in material science. And also this is oxidation. Uh, Essentially, this model is widely applicable to different gas-liquid reactions, and we just consider oxidation here. So we consider the different locations will have different temperature, different chemical combinations. So the oxidation rate will be different. And also there are some initial oxides in the material. So these oxides from the original one and also the oxidized one, they will redistribute it along this multiple flow, and then in turn they will influence the surface tension coefficients. Then in turn they will influence the multiple flow. So we investigated different um, uh, alloy systems and also different uh, ambient environment, say high oxygen content and low oxygen content. These are some experimental validation here. Um, so I will maybe here we also consider the evaporation of the oxide. So that means at this high temperature, not just the material itself will evaporate, its oxides will also evaporate. And if the oxide evaporation rate is higher than the oxidation rate, that means there will be overall reduction of the oxygen content in the material. So this is one case. You can see initially the oxygen content is about 2000 ppm, but after laser melting, it's reduced to about 100 ppm because uh, again, different locations have different temperature and different chemical compositions will have different evaporation rates. And they have a balance of, they have a competition with the oxidation rate. And for different materials, certainly it will be different. So I'll skip this. This one is uh, a case for composites. So the gray particles are tungsten particles, which have higher density and very much higher melting temperature. The others are copper, and we intentionally select the manufacturing parameters so that tungsten particles will not be melted, and copper will be melted. And you can see these tungsten particles are floating on the multiple surface of copper. But tungsten density is much higher than copper. Why are they not sinking down? Uh, because in this scale, tens of micrometer, the surface tension is dominant, and gravity and buoyancy are, are minor compared to surface tension. So you can see this is experimental validation. After solidification, most of these tungsten particles are still on the surface, so which validate our simulation. And for nanoparticle reinforced composites, is a different story because size effect. Okay, so these gray particles are the clusters of nanoparticles because our model resolution cannot resolve such fine nanoparticle. Um, okay, but when we do this simulation, because the motivation is our collaborator, they do this experiments and they found these nanoparticles can hardly be uniform. So we do the simulation to help them. So when we run the simulation, we found generally the at the middle bottom of the molten pool, there will be fewer nanoparticles. Near the two edges, there will be more nanoparticles. And this is because of the Marangoni flow and also the centrifugal force due to the vertex. So here, uh, after we understand the mechanism, we can easily solve it. So we just make sure this one is the center of the second track. So this will be the edge of the second track. So these two regions will be automatically averaged. So we do the simulation here, and you see it's become more uniform here. And then we just scan the third track centered here, and then this is will be center, this will be the edge, then they will be averaged again. So after many layers, many tracks, um, the overall distribution of nanoparticles will be pretty uniform. And you can see this is the experimental results following our suggestions, which results very good mechanical properties because the distribution is very uniform. Um, Here, we develop another model. We consider the influence of static magnetic field. So we consider the Ohm's law and Seebeck's effects, which will generate very weak electric current. And this very weak electrical current and a strong magnetic force, and a strong magnetic field will generate Lorentz force. And this Lorentz force will influence the molten flow. So we run different cases, no magnetic field, 0.4 Tesla along y direction, 0.4 Tesla along z direction. Um, then we got this results. Uh, the major finding is here. The multiple flow patterns uh, become very different. So without magnetic field, there are two vertexes, one here and one here. So when there's a bubble generated from the keyhole clap here, the bubble will be circulating with the vertexes, cannot escape. So the porosity will always be there. But with external magnetic field, the vertexes will be eliminated, especially like one. So when there's a bubble formed here, the bubble will flow out, will escape along this streamline. So it can reduce the porosity, which explains the long-standing experimental results. Um, and also, the Lorentz force can be strong enough to change the grain structure. But I will not go into details here. So after this multiple simulation, uh, we further implement the temperature field into the grain growth model, where we consider the nucleation uh, depending on the local chemical compositions and local temperature, also cooling rate. And these are potential nucleation sites. And then there are also epitaxial growth. Uh, There will be competition between the nucleation Gruen growth and epitaxial growth. And this is the simulation results. Mostly the epitaxial growth is dominant. As a result, people try to, as a result, mostly in additive manufacturing is common Gruen, which result in anisotropic mechanical property. So people try to refine the Gruens by adding nanoparticles. Uh, so um, then we also see when we add nanoparticles in the phase field, we can increase the nucleation size and also the um, uh, can slow down the grain growth rate because of the Zener pinning effect. And these are simulation results. Without nanoparticles, the epitaxial growth is dominant, so it's mostly columnar grains. And with nanoparticles, um, the near the edge is still columnar grain, but it's slowed down by the Zener pinning effect, and there will be a lot of nucleation size in the middle. So it become equiaxial grains in the middle. So there's some experimental validation and some statistical analysis. Um, so I just quickly uh, go to here. Lastly is mechanical property. So we implement the temperature profile and grain evolution into the crystal plasticity model. We simulate the thermal stress formation by considering different grains will have different temperature, so they have different thermal expansion or shrinkage. So they will generate macro scale thermal stress, and then we simulate the cooling process. After that, we got the residual stress. Finally, we simulate the tensile behavior with reduced stress. And then we validate against the in-situ tensile experiments by Lawrence Livermore National Lab. So this is experimental validation, and you can see different grains. There are different thermal stresses and reduced stresses. And then we also simulate the dislocation evolution in different grains, different locations because of the thermal stress. That means stress loading and temperature. So this is the stress evolution, and also some experimental validation. Uh, uh, Let me go directly to the last page. Okay, so overall, this is the workflow we previously developed. So this is like one directional coupling with similar the multiple flow, and then to the uh, microstructure evolution, and then we simulate the thermal stress. So that's basically our current model, but some reflections maybe it's bidirectional or coupling. So from here to here, maybe it's minor, but from this thermal stress to Green evolution, there are more questions to answer. And then also the Green growth may also influence the multiple flow. So I will just stop here. Thanks.
Thank you, Wentao, for the great talk. So we will save questions for the end of both talks. So our next speaker is Prof. Steve WaiChing Sun from Columbia University, where he's an associate professor of civil engineering and mechanics. And he obtained his bachelor from UC Davis and his master in civil engineering from Stanford, along with an MA degree from Princeton and PhD in theoretical and applied mechanics from Northwestern University. So, Wei-Ching, the floor is yours. Thank you.
Okay, thank you, thank you. Thank you everyone. Thank you for either wake up really early or stay really late for this for listen to this talk. So today I want to talk about new research I have on modeling complex geometry with material model. So I think all of us knowing that there is an ingredient for physical simulations, which is the governing equations. The governing equations could coming from the balance of balance principle and also the material law. And as we can see, there's an example of the logic or the direction graph that representing the computational model. In a displacement-based finite element, we may have a displacement getting the strain and stress and balance of linear momentum, which we can do it in we can simulate those models in a classical commercial code. But for solid mechanics, the issue is often not in finding the constitutive law or the balance principle, it's on the geometry. How to represent the geometry and how to solve the boundary value problem. The key here is that sometimes they have a slightly different demand. So shown here is actually not from my research, but from the work from Oxford with the geometrical pyre. If you can see here, the horse can be represented by point cloud, by graph, by mesh. But notice that there is a slightly difference on the representing geometrically what we need to put the point there and what we actually need to have the sufficient resolutions for the boundary value problem. For example, if I have a heat source or I loading this horse structure, I may have a stress concentration that geometrically there is nothing interesting, but I would need a very fine mesh. Or put it on the other way, if you try to represent this horse in a very perfect manner, I would have some very tiny element to model the eyelids or maybe the nose. And those things are actually really hard to resource because it needs a very high conditional number to solve in a conventional finite element. So the idea we want to try is that is it possible to separate the need for the geometry to have very fine mesh while we can actually still capturing the necessary geometry effect while addressing the need for giving enough freedom for our solution field. So this is actually the classical issue about the meshing. If you work in Sandia or other national lab, we know that we actually would have to spend a lot of time on meshing in addition to solving the boundary value problem. Here we want to actually do something that are actually very close to the meshing, but we want to use the neural network to replacing the process of meshing in our numerical model. So this is actually inspired from this isoparametric mapping. I think for all of us learn the finite element, we know what it is. Basically, is a mapping that allows us to attach one element geometry to a reference geometry that will never change. Now, the idea that we want to actually attempt is that if you actually don't want to mesh an individual element with isoparametric mapping, but we want to map a global domain into a single reference shape, is it possible? Or maybe in a multiple shape, is it possible? So this is actually coming from the idea of representing metaphor. Shown here is actually just what we see from Wikipedia. And what we actually see is actually a domain that are parameterized by different subdomain, or actually we can call it patch. And what we actually have is the following. For each of the coordinate chart, which is actually the U, we want to actually establish the mapping that can map to reference configurations and then have the inverse that allow us to map into the background. Now, what we are actually interested is to do the following. If I have a geometry and I actually using the neural network to learn all those mapping, is it possible for us to representing the geometry? Now, in the classical way of creating atlas, this is actually like collections of the coordinate chart. We may actually have the overlapping domain, and then in between that, this constitute a transition map. As you can see, if we successfully constitute or parameterizing the entire metaphor into a collection of the coordinate chart, we need to make sure that the transitions is actually working, and then the inverse between them always exists. Now, this actually could be used as the learning problem in a supervised setting to actually representing the geometry. And in this case, we use the Stanford bunny as a demonstration example. In the real case, there are more than 3 collisional charts. We tried it with 8 or 10. The idea is the following. Can we actually decompose the geometry like the Stanford bunny into multiple coordinate chart and establish the mapping? And to solve the boundary value problem, instead of having a really difficult mesh and solve the classical Laplacian problem, can we actually using the mapping to map the governing equations onto the reference domain and solve the governing equation there? And that is actually the whole idea. And in order to do that, we actually need to ensure a model thing. First, we need to actually knowing that the Jacobian exists and the inverse of the Jacobian also exists. And we also need to able to do calculus in the reference domain. Our governing equations, for example, the Poisson's equation, the balance of linear momentum is in the actual physical domain. But what we actually want to do is to map it into a reference mesh that will never change with different geometry. And what we actually want to do is using the AI to establishing the mapping. And we also want to ensure that the transition map are actually consistent to each other, meaning that if I actually moving this point from chart A to chart B, I don't actually want to suddenly have a jump or actually inconsistent, and we want to ensure the communications. And this is actually also another interesting factor, because if we actually decompose a domain into a set of the coordinate chart, we can actually using the classical domain decomposition method that are applied in those overlap plot, and or for example using alternating swap method to actually capture the governing equation of the entire domain in solving it in a decoupled manner. So this is actually some of the details algebra, as you know from the continuum mechanics. What we actually need to establish a lot of time to establish the governing equation is actually establish the pullback of the gradient, the polar flux that actually tell us what if we map it back and map it forward, what is the relationship between the two. And we actually also want the normal mapping that are simply telling us that what is the new coordination system after we actually transfer from the physical domain to the reference domain. If you're actually summarizing it, we actually can rewrite our domain into the governing equation of our domain in the distorted or actually into the reference configurations. The idea again here is that we actually don't want to do the mapping. So instead of actually we don't want to do the matching. So instead of the matching, we will actually map it to the reference, but the price we need to pay is that we need to solving the governing equations in the reference configurations, and this is actually lead to this set of new governing equations that we actually need to solve the equation there. To actually ensure that the mapping is success, this is actually some of the construction laws. As you can see, this is actually pretty common. If you actually look at the collision chart, we actually want the mapping actually exist, and we want to make sure that if we map it forward and backward, we get back to the original point. And we actually also want to make sure that if we have assigned distance functions, that things point are inside remain inside and outside remain outside. And we want to actually have each of the coordinate chart covered by enough point. And we will actually also want the Jacobian to exist, because otherwise there's no way we can linearizing the problem. So this actually leads to a multi-objective optimization problem that are actually used to learn the coordinate chart. We can think about it as the supervised learning problem that are replacing the meshing procedure in order to get the coordinate chart representing the geometry. So this is actually giving one example of a divergent form. As you actually know, this probably is very familiar. If you actually have some kind of divergent property, this is actually what happened in the governing equations. we actually map it back into the reference, and then we actually have to take out the size of the Jacobian, and then actually we normalizing it. Then we actually get to representing the new residual in the coordinate chart coordinate system. Also, we actually check our idea. This is actually very simple. We actually have analytical solutions that are actually for the ellipsoidal, and we actually create the mapping that mapping into a circle, and then we actually see whether that that is actually possible to solving it analytically. Solving it in a pin system. So this is actually the exact solutions. We already know the analytical solution. There is not that much point to solving it there, except to check whether the solution is actually correct. And in this case, we did not change it for too much, just 1 minute, and we can achieve a pretty good result. This is not surprising because the solution field is actually not that complicated. It's just a very classical or Poisson equation problem with manufacturer solutions. The second problem is actually also on the verification problem where we use another manufacturer solutions. This is actually the Poisson equations. If you actually obtain the Laplacian, this one cancel out, and we actually just want to use to check whether the collision chart is actually working. So the first thing is that we need to use the level set to reconstructing the collision chart. This is an 8-chart problem. So basically the Stanford bunny is decomposed into 8 components, and we want to check whether the Jacobian would go to 0. If this is the case, then it's degenerating the volume into a surface or actually into a line, and the whole thing doesn't work. You can actually see that the solving the multi-objective problem to reparameterizing it to the collision chart is actually not exactly easy, but it could be manageable. In our particular problem, we also purposely control the try to reduce the condition number, which is actually the largest eigenvalue derived a singular value derived by the smallest eigenvalue of the Jacobian. And we can see that is actually not that bad. I guess they are remain in the first order simply because reducing the collision chart as much as it can is actually in the criteria of our calculations. And we can actually see some chart actually cover more point and some less. And then here is actually the transition map to making sure that in the overlap regions there is not that much mismatch between the collision chart. But assuming that this training, this benchmark are actually passed, then the collision chart is ready to representing the geometry. In this particular case, we use a partition of unity to actually get back the global equation. So this is actually the partition values in the transition zone. And if you calculate, if you actually look at it, we can actually see the chart, the boundary, the chart where are the overlapping zone in this case. Also, we tried it in pin. This is actually the L2 error of the governing equations. We actually did not fine-tune the pin very hard. Otherwise, we may actually able to get the solution better. So in the pin case, we're using the multiplicative swap coupling, basically solving one domain and then another domain, and introducing a coupling to ensure that the transition is actually stable. But what we actually find surprisingly is that if you have the collision chart, we can just simply solving it in the classical finite element in the reference domain. And in the finite element, the control of the accuracy is easier, although you see some of the pattern that some error did exist. And I want to say that this is actually depends on what reference check did we use. If you're actually using the cubic, the issue of the Jacobian is that in the corner and in the edge, you will get a bifurcation of the gradient. So we have to smoothing it, the cubic into the smoothen versions, or you can use a circle or the spherical object as a reference check, and then formulating the map problem in a spherical coordinate. The issue is that the North Pole is actually singular, so there's some trade-off in those reference check choice that actually we can actually see here. But the key here is that we find that in general, even if we just did not do anything special with the finite element, as soon as we refining the reference shape, we actually get back the classical guarantee for the linear finite element, which is actually OH2. This is actually what we want to check the implementation that are correct. There is the one downside for that method, though, is that compared to the classical finite element, because how dense the tangential matrix it is would actually depend on the depends on the mapping. If there's a loss of shear or distortions, you would expecting the Jacobian have a loss of off-diagonal term, and hence the resultant tangent would not be as sparse as it is. But overall, you can see that this is actually working, and then the coercive track communications also provide optimal opportunity for domain decoupling. We also solve this problem, and then this is actually just to showcase why we need more than one coercive track. So in principle, we only need one coercive track to actually mapping the rabbit. That is actually because it's a simply connected body. However, in this donut case, we would actually find that we cannot cover with one coercive track. This is actually because of the topological difference between the two. And in this case, we use, I forget in this case, I think it's 8 coercive track to actually map each portions of the donut shape. And we actually solving the J2 plasticity both forwardly and inwardly to actually see whether this geometrical shape that we actually represent by the coercive track can be used also for the inverse problem. So this is actually a J2 von Mises plasticity with a kinematic hardening. So we actually want to know whether we can actually using this technique to recover the back stress, and from the back stress, whether we can actually back calculating the kinematic hardening coefficient and the initial yield surface. There's some difficulty there, and my student actually find that technique is that in the case of the inverse problem, if we're actually solving the elastoplasticity problem, the bench vector have a jump here, and that actually make the inverse problem really hard. And what they are actually doing is to introduce regularizations. So in this case, we adopt this technique there, and then we actually recover the yield stress, which is actually lead to the von Mises and also the hardening. I also want to motivate it a little bit because of why we are doing that. That is actually stimulate the interest is actually come from another research which recently published in the PNAS. And that research is actually using differential simulations to actually recover the constitutive law here. In this case, we have a neural network to present a material model, in this case a yield surface, and we have the digital image correlations that are either real or from the subscale simulations, just to benchmark the results, or maybe not subscale, just a benchmark ground truth. And what we actually want to do is that can we matching the displacement field by actually changing the constitutive law, and from that can we recover the model. The key here is that this could be done both for the cohesive zone law and for the bulk material law. But the key here is that it needs to be really smooth, and the simulation need to be differentiable, because otherwise the back propagations of the neural network won't work. In this case, my student actually using the NVIDIA package whip, and we actually ensuring that using the trick we mentioned previously to ensure the smoothness of the finite element, by actually ensuring that the gradient actually exceeds in our model. And this is actually done in a very simple way. In a classical way, we have a elastoplasticity jump, and that lead to the Heaviside function to representing the yielding, and then after the yielding, it changes to a branch behavior. Unloading, we get elasticity, and then if we have a plasticity, we actually have the plastic flow start to develop. It's a switch. In our case, we're actually changing that heavy side function into a smooth approximations, and that make it the Gaffney equation differentiable. And how sharp the Gaffney equation it is controlled by this parameter for the H2. So this is actually an interesting work in the sense that sometime we want to design a very complicated machines to allow us to loading the material in many different ways. But here the interesting question that we find is that is it possible to think backward if we have machines that have very limited type of loading? Can we design the geometry so that it give us a sufficiently rich stress field or then displacement field so that we can recover the constitutive law. So and for that, then of course we need to using construct an inverse problem that isn't too sensitive to the meshing technique. As you know, if you actually do the material discovery before, different mesh may give you a different shear modulus or buck modulus, etc., etc. And what we actually hope is that the new network approach, if it's actually changed successfully, can actually bypass some of the dependence of the mesh and actually help us recover the constitutive law. And I want to say that what we focus on is just one piece of geometrical structure, but also there are times where we have assembled like composite or actually polymer bond material that we have multiple inclusion with very interesting geometry. In this case, the goal is not necessarily just representing the geometry, but how things connect. And we also have another work that are actually introducing a generative graph to create a realistic looking graph. And from that, we actually put the inclusion there. So this is actually one example of using that to actually to guess what is a small particle that only have one voxel left in a micro CD image. We will open source the code. The paper is actually under review. I don't know how this will go. But our goal is, my intention is that if the paper is accepted, I would open source the code, and I think that yeah, I think that we'll see what happens. So anyway, I just want to say it's exciting time for computational mechanics that we can see, and I think that we have a lot of new tools there, and many of us are confused. But some of them are actually, I find it quite useful, and with particularly if clearly strategy are put into those tools, I think that this is actually helpful on discover mechanics. In a sense, it's like before we are trying to walk, but right now we have a car to drive. Doesn't mean the car is safe. It can actually crash. But if you're using the tools properly, that could actually lead to something interesting. In this particular case, part of the deviation are actually checked by the crowd coding agents, and this is actually so there's two potentials as well as a trap in the future of using the generative model. So I think that's it. So thank you for listening again. I know it's I hope you did not feel bad for missing your dinner in a prescribed time or breakfast. And thank you.
Thank you, Steve. Amazing talk. And well, the floor is open for questions. Any questions?
Maybe may I ask a question? So Steve, yeah, nice presentation. I have a question about you mentioned you try to smooth the plasticity law, right? So will that create maybe like say a different, I mean, firstly, how do you control, like say how smooth are you going to do it?
Yeah, it's just a regularized heavy side function. So you can actually always represent approximate heavy side function with sharp gradient, or controlling the gradient or
Yeah,
curvature you
right.
want to have. Then of course it's not really a jump. So in a very regular sense, you actually are creating a small zone that have a transitions
Yeah,
between
right.
plastic
That's
and
what.
plastic. So it
Yeah.
doesn't really make sense. However, for the purpose of identifying the material parameter, if you can actually controlling it or fine tune it or actually do a systematic refinement to approaching it back into the jump, and you can see how robust the result is. The thing is that
Okay.
without that, you have a gradient explosion, so it doesn't really work for back propagations. And I would say that in the old days, this is not a new problem. The topological optimization community would actually using finite difference to actually bypassing it. But the trick is similar. So you basically are avoiding the jump by saying that, hey, I actually let me not sampling the jump and go a little bit further and get a gradient. But I think a smoother approach that exists everywhere is better than the finite difference in terms of being more robust. At least you can actually tune the regular heavy side functions to see whether it converge, or in some cases it could diverge. So this is also the important thing to know.
I see. So basically, that's kind of can be treated as a hyperparameter, so somewhat like tunable in some
Yeah. It also
way.
depends on for the plasticity example, it really depends on what you're trying to do, what you're trying to achieve, right? I mean, and this jump can also occur not only in the isoplastic branch vector, but also some U function like crystal plasticity. They simply have a corner just because you have a slip system activate. So these are physical. If you're smoothing it, we will not be as accurate as you have a jump, but also you don't have bifurcation. You replace the bifurcation with something change very rapidly. Yeah, but this depends on the whether you want to use the differentiable simulations. I mean, if you're not, then I think there's also another approach is to simply identify where is the edge. You basically solve a classification problem to saying that where is the edge, you put a line there, and then that would also solve the problem. But by actually cutting the domain into a different subsection. But of course, the classification problem of the exact location, not classification problem,
Yeah, usually there's also
to find out
some.
the exact location of the edge without knowing that whether it exists is actually a very high dimensional problem, and that is not always feasible. If you know you're actually doing a crystal and you know the symmetry, this is actually quite feasible. You just need to rotate and see whether it match. So
I see.
it depends on what problem. Yeah.
Yeah, I see. Yeah, I think that's a fantastic idea
Yeah.
to make the function differentiable, and then it's more trainable. Yeah. Thanks a lot for the detailed explanation. Thank you.
Thank you.
Any other questions? Guillermo, I think you have one.
Yeah, I had a more basic question. So let me try to understand. I mean, I'm not an expert in neural networks, so this is for maybe less expert guy. So you are learning the geometry, and let me ask you one question. Are you learning that particular geometry or any geometry?
Sorry, can you say it again?
For example, are you learning the geometry of the rabbit in your the bunny in your example?
Yeah.
Or you are learning, or you do a pre-processing in which you learn, given a cloud of points, any geometry?
So for different problem, you need to actually create the learning problems from scratch. This is simply representing the meshing. And what we're actually doing is not necessary. We are not learning the geometry of the rabbit. We are learning the mapping, the deformation.
Yeah. No, I understand. That part I understood. So okay. That was my question. And then you build a pin on top of it. Now that you can handle. No, but look, I totally see the value of this work, because eventually, geometry is, I think from my perspective, geometry is at least a half the space, because the other half is materials.
Yeah. And also another thing I actually always have this problem is that I have those geometry that have a lot of details, but I actually doesn't have factor or plasticity there. So I really don't want to waste the degree of freedom to actually just get and then have to deal with a high conditional number just to deal with, just to make sure that the nose or the feather of the weapon is actually there. When from the solution field point of view, there's nothing there. It's just almost nothing. So for that
it's
case,
very interesting. Very interesting. Thank you.
Yeah, thank you.
So then I have a question for Jan Wentao. So impressive work. I wanted to just have a general sense from you, since you're working both at the computational level, but also very deeply at the modeling level. What is your sense? I mean, in terms of the field of additive manufacturing, the biggest gains are to be made by improving models, the modeling, those aspects, or you still see from the computational aspect, have you run into situation in which changing the representation of some of the geometric features or anyway using a different computational method makes the biggest difference? What is the balance in your opinion?
Okay, so thanks for the question. It's it's a very good question. From my understanding, I would say, so I try to implement the most suitable, most efficient computational methods in additive manufacturing, right? So I tried quite a few, including material point method. I try to solve the solid mechanics problem and fluid mechanics problem in one framework, which free method can do pretty well. But when I try the first simulation, the computational cost was super high. I cannot even run one time step within one day. So then I have to decouple all this model into different models. Then do this linking instead of solving all the problem in one model. So I would say um, the advancement of new computational methods will certainly advance this modeling for additive manufacturing. But currently, this additive manufacturing mostly they want to have reliable and high efficiency computational methods. So mostly it's still very classical ones like finite element method, finite volume method, um, then cellular automaton, feed
Volume of
field,
fluid,
discrete element methods, all these um, classical ones. But actually, we made some improvement into these models. For example, we add some new physics, and also we improve this surface tracking, free surface tracking methods in different models.
So this is basically aligned with what I was asking you. Basically, so let me tell you some of my experience from San Diego National Laboratories. I used to work there. And there was a season, I think the 90s, for some class of shock physics problems in which the physical model, the material, having better material models in the simulation was making the biggest difference. And that's where all the money was going. But there were also other phases in which once they managed to make the biggest gains with improving material models, then they started taking a look back at the numerical methods because they started they sort of discovered the limit of some of the computational methods. Like if you're making an 80% error or more just because of the material model, honestly, quadratic accuracy doesn't really matter. But the moment you get to the 10% regime, then maybe you can start seeing a difference. And I think you answered my question in multiple ways.
And actually also So firstly, we want to make sure the simulation, the models are reliable and accurate. Then we want to improve the speed. So actually, but you know, in a lot of industry applications, people do not really trust black box machine learning approach. So you have to make sure your models are explainable. So we're also trying to improve the computational efficiency. But the condition is we have to incorporate physical laws in the model.
Thank you.
Okay, good. So any last questions?
Can I
I
ask a
do have
question?
one, if that's okay. Or I'm a little bit, this is for Professor Sun, if that's okay. I'm bear with me because I'm a little bit ignorant to a lot of machine learning, and also I think bear with me also if this is something you've already mentioned before. But when you're trying to use machine learning to learn in particular the charts of the geometry, is all you need just that point cloud? Because normally when we think of like shapes, we think of like it's like smooth and connected and stuff. Is the point cloud that you suspect comes from a manifold all you need?
Well, I mean, if you have the point cloud that without the noise and everything, then the point cloud is actually the starting point, would be a good starting point. I mean, if the geometry represent adequately, it doesn't really matter. It could be a parametric surface, it could be a mesh, it could be a level set. In our case, I always use the level set just because if you define a surface in the with a level set, and the level set is parametrizing with some bases that are smooth, the solution exists everywhere, so I can sample as much as I want or calculating the gradient. If you do using it with the point cloud, the issue is that there is no gradient exactly. We can recover it from some PCA gradient, but that would actually introduce some other hyperparameter or issue to consider. So in our case, we all train it with the level set. Even if the point cloud, we convert it into the level set, solving some. Well, you can reconstruct the level set reinitialization problem to converge the point cloud into a transition function problem or stuff like that. Or you can actually converge a voxel into a level set. So but that being said, I think the major issue is not necessarily the type of representation, but the quality of the representations.
I see.
As you can see, if you map it from the ellipsoidal to circle, there's no issue almost just because of the analytical solution of both exists, and I know the analytical solution of the mapping. For the web, but as you can see, some portion are pretty easy to map, some portion are really difficult, like the ear part. You can easily get a really terrible. Then you actually need to think about how many coordinate chart, how to connect it to give you the upshot. But this actually could also be done in a dynamical way. If you have a fracture, you're changing the topology, then you can also add a spawning, a coordinate chart, etc., etc. That could also be done. The coordinate chart actually are sensitive to what kind of geometry and what type of topology you want to represent. But anyway, but in this study, I'm just doing it try and error. I did not really rigorously thinking about how to optimizing the locations and size of the coordinate chart, simply because I would say that the Stanford Bunny is not an easy geometry, but also not super hard compared to the other one in the benchmark.
Yeah, for sure. Thank you for that.
Yeah.
Yeah, Beijing Chen, I think you had a question.
Yeah, thank you. I appreciate. I have a quick question for Professor Song. And by the way, I'm also from Colombia, and nice to meet you virtually. And so I remember later half of your talk, you briefly presented some of your work on using neural networks to predict or discover elastoplasticity. I'm actually doing consumer modeling side. So my high level question is like nowadays with AI wave, for what do you see, like how the AI or like the data-driven or machine learning neural networks combined with consumer modeling develop or goals in 5 years or 10 years? Because nowadays I feel like neural networks to some sense it's like black box, a fitting tool without I feel like it's not very interpretable. So do you really think neural networks can develop in some ways to really help people to discover better physics or better constitutive laws?
I mean, so what I'm trying to do on the constitutive law work is I'm trying to pick those models that have a geometrical meaning, like a U surface, a hyperelasticity, where the geometry or the smoothness of the gradient of it has some physical meaning. So if you're actually parameterizing those models in some kind of geometrical inspired model, then you can easily interpret it. For example, in the U surface, the corner represent a job bifurcation of the plastic flow. There is a physical meaning on that of a slip system, or you can actually check the polyconvex or hyperelasticity model. So incorporating a physics is always an important problem. From the machine learning community, there's always a debate, should you explicitly put it there, or because the data already have the physics, you just need to have more data so that the behavior of the physics can emerge. And I think that depends on the data. I mean, in the longer future, I really don't know what will be in the longer future. I think things are changing so fast. But as you can see, initially, a couple years back, a lot of the method that are based on the machine learning are basically PIN or physics informed neural network or other things that are actually very different from the conventional modeling. But I think I can predict in the short horizon with the large language model, they read a lot of literature. I think lots of machine learning application will be more conventional simply because the large language model have read enough classical literature. That doesn't mean that the very game-changing method won't exist or something that completely change the paradigm. But I think that there is a lot of room to reach the plateau on how the different ideas are combined simply because if you build an agent, they can actually explore continuously and find those opportunity. I think in the longer horizon, those low-hanging fruit will be taken. And then that would be the interesting point to see the longer future. I mean, right, I think what I would see in the short future is that a lot of incremental improvement will emerge from the literature, and in the longer horizon, I think that it's harder to tell. Maybe something very different would actually show up. But yeah. Anyway, it's a very difficult question, so I don't really have I don't have that kind of a pay grade to really anticipate. It also depends on the government funding. Yeah, but I do think that in the short run, the model that can leverage the agents would actually work. In the longer horizon, there is also work for machine learning to build a role model. Then we will see what happens about whether this thing would actually be success. But right now, I'm not really understanding that completely, so I cannot comment too much.
All right. Thank you.
Thank you.
Okay. Well, thank you, Steve, and thank you, Wentao.